Okay, so we're getting pretty close to time for the next talk. Let me remind you that this is the last talk of this session 3 afternoon session. Afterwards, we have about a half-hour break. And then for the principal lecture by Jessica Purcell, you're going to want to go report to the Zoom room for session 1. So the session 1 Zoom room is where the principal lectures will be each day. Okay, so with that, it is time for us to get started for the last talk of this afternoon session. You ready to go, Didac?
Yeah, I am.
Okay, yeah. All right. So it's a pleasure to introduce Didac Martinez-Granado of UC Davis, who will be speaking on volume bounds for a random canonical lift complement. So it's all yours.
Okay, great. So thank you very much for giving me the opportunity to give a talk in this session. Today, I would like to talk about a joint project with Tommaso Cremaschi, Yannick, Krifka, and Franco, Vargas, Pallete on giving lower bounds on certain three manifolds obtained by taking complements of canonical leaves. So let me first start by saying some general words on how this talk is going to relate to the main lecture today. So by Jessica. So Jessica, one of the things that will be discussed in the main lecture is how to go from combinatorial topological descriptions of three manifolds and extract geometric information of those. So for example, give lower bounds or upper bounds of the volume of a given three manifold, starting from topological data. So going from three-dimensional topology to some invariant in three-dimensional geometry, such as volume. And in my talk, what I want to do is I want to start with two-dimensional geometry, so curves on surfaces, geodesics on hyperbolic surfaces. And I want to use that data to construct a hyperbolic three-manifold and then try to study the volume of that three-manifold by comparing it to geometric information that comes from the two-dimensional geometry. Okay, so I want to study the interplay between the starting data in the two-dimensional geometry world and the corresponding volume of this three-manifold that I will obtain. So let me tell you how I can construct a three-manifold starting from some geometric information on a surface. So the ambient three-manifold that I'm going to be considering is the unitangent bundle. That's not the ultimate three-manifold that I will consider, but I'm going to start with a unitangent bundle of a closed hyperbolic surface. Okay. So let X be a closed hyperbolic surface, and let me consider the unitangent bundle, which is a three-manifold where I consider pairs of points on the surface together with a unit norm vector based on that point. Okay, and I'm going to be calling this pair V. So here you have the surface X. Here I have a point on the surface together with a unit vector on the surface. So given closed geodesic gamma on the surface X, such as this geodesic gamma here, I can consider its canonical lift to the unit tangent bundle, where I equip the closed geodesic with the unit vector at each point corresponding to the tangent vector to the geodesic at that point, the unit tangent vector. Okay, so that's what I call a canonical lift of gamma. So gamma is a geodesic on X, and I consider its canonical lift in the unit tangent bundle. So now, in general, given a three-manifold M and a link or a knot inside of that three-manifold, I can drill the knot or link from that three-manifold by removing a tubular neighborhood from the three-manifold, and then I obtain a new three-manifold with boundary. So let me do this with the unitangent bundle. So let M be the unitangent bundle, and let K, the knot in question, to be the canonical lift of a closed geodesic on the surface. So the canonical lift of this closed geodesic is some knot inside of the unitangent bundle, and I can drill it out of the unitangent bundle. And the resulting three-manifold with boundary that I obtain, I'm going to call it M sub gamma. So it's from a closed geodesic gamma on a surface, I obtain a three-manifold. theorem by Eiffel and Hasselblad tells me that, in fact, if gamma is a multi-curve or a collection of closed geodesics on a hyperbolic surface such that the collection or the closed curve is filling, primitive, and in minimal position. So if, for example, gamma is a geodesic that is filling and primitive, then this three manifold that I obtain is in fact hyperbolic. Okay. So starting from a closed geodesic on X, if I assume that this closed geodesic is moreover filling, I can ensure that the corresponding three manifold is hyperbolic. And this hyperbolic three manifold M gamma has some properties. So for example, this construction that I outline only depends on the, so does not depend on the choice, the homeomorphism type of this three manifold does not depend on the choice of the hyperbolic structure X on the surface that I started with. And in fact, it only depends on the curve gamma up to homeomorphism type, in the sense that if I have two curves gamma and gamma naught, which are related by a homeomorphism of the surface, then the corresponding three manifold M gamma that I obtain is homeomorphic. And in fact, I then obtained by most of rigidity isometric three manifolds, and therefore their volumes have to be the same. So this is going to be the main object in this talk. So starting with a closed geodesic, I produced closed filling geodesic, I produced three manifold, which is just hyperbolic. And now I would like to study the volume of this three manifold and relate it to some geometric information of the closed geodesic gamma that measures the complexity of the geodesic gamma, such as, for example, the hyperbolic length of gamma. Okay, so let me give you some examples on what you can expect for, in general, for some collections of curves. So you can have collections of curves for which the length blows up, goes to infinity, whereas the volume stays bounded. And here's an easy example on how to construct such a thing. So start with a closed filling geodesic on the surface and hit it with an infinite order mapping class, like a pseudo-anosov, for example. And then you will obtain a sequence of closed geodesics whose length goes to infinity, whereas their volumes stay constant because the corresponding curves that you get by applying the mapping class are, of course, in the same homomorphism type. So in general, you can have length going to infinity, whereas volume stays constant in this case. There are more interesting examples. Rodriguez Migueles shows that you can get other examples, explicit constructions of sequences of curves with manifolds that are pairwise non-homeomorphic, yet their volumes stay bounded and their length go to infinity. And he also constructs families, explicit families of filling curves for which both the length and the volume blow up, they go to infinity. And in fact, he can show for those collections that the volume grows at least sublinearly as a function of the length. Okay, so these are some examples for some explicit constructions of families of curves. But what is our result? So in our result, we wanted to get a grasp on what happens for a generic closed geodesic. So for some definition of closed geodesic, if I pick a closed geodesic at random, what can I expect for its volume? How is it going to grow? Is it going to stay bounded? If it doesn't stay bounded, how does it grow as a function of the hyperbolic length? So that's the kind of question that we would like to study here. And what can we show? Well, first of all, I need to tell you what model of random geodesic we pick. So what do we mean by generic geodesic or random closed geodesic? So here's one model that one can give that has been considered before. So take your surface X and pick a sample of unit tangent vector V uniformly at random. So you pick a point of the unit tangent bundle at random with respect to the Liouville measure. And then flow by following the trajectory of the geodesic flow for a long time t until you get back close to where you started in the unit tangent bundle. Then you can close off this trajectory by some short arc, and then you get a closed curve on the surface. which if you want, you can pull tight to a closed geodesic. And then this closed geodesic might not be primitive, but you can take a primitive subcurve. It turns out that for T large enough, one can show that this geodesic that one obtains is actually filling. And this follows by some facts about the dynamics of the geodesic flow, as well as that can be formalized using the language of geodesic currents. So one way to say that is that if you think about this sequence of curves scaled by their hyperbolic length, and think of them as Didac measures, in the sense of measures, this sequence of measures converges to the volume measure. And that tells you that the corresponding collection of curves has to be eventually filling. So we constructed some model that for a random point in the unitangent bundle, that is with respect to the Liouville measure, gives us a closed geodesic or a sequence of closed geodesics, which we know that are filling. And so what we can prove about the volume of these corresponding three manifolds for these closed geodesics is that their volume grows at least like a function of order squared of t, where you can think of t as the length of the corresponding curve. Okay, so we can give a lower bound of the type squared of t. So that's the main statement that I wanted to present. And so I wanted to make a couple of remarks about this statement, just to contrast with other results. So first of all, is that in general, there is a general upper bound on the volume for the volume of canonical lifts. So by Bergeron, Pinsky, and Silverman, they proved that, in fact, for any filling closed geodesic, if you look at the volume of the corresponding three manifold that you obtain, that volume is bounded by a linear function of the hyperbolic length of the curve. So what our result is saying, it's giving a lower bound in the other direction. So the optimal growth follows that it stays somewhere between square root of the length and the length. And also I wanted to contrast this with the setting of alternating lifts. So we are looking at canonical lifts here, but in general, one can consider other types of lifts, topological lifts of a curve to unitangent bundle. And for alternating lifts, one can construct examples where the volume of the corresponding three manifold grows like the self-intersection number of the curve. So in particular, it grows like length squared. So the volume grows much faster as a function of the length for alternating lifts, at least for some examples. So I'd like to say a few words about the proof, and I'm going to be talking about two main ingredients very briefly. So the first ingredient is we use a lower bound, a combinatorial lower bound that was proved by Rodriguez-Migueles, and I would like to briefly say what that is. So let's start with the surface and pick a pair of pans of composition. And let's consider our curve gamma. So in this picture, the pair of pans of composition is depicted using green, and the curve gamma in question is this curve gamma in red. We say that what is a gamma arc? A gamma arc is just the intersection of our curve gamma with one of the pair of pans in minimal position. So in this picture, this arc, this blue arc here would be a gamma arc. And we consider gamma arcs up to free homotopy relative to the boundary. So endpoints of these arcs have to stay in the boundary, but we are allowed to glide them. So they can glide along the boundary. To give you a concrete example, suppose that we are only focusing for now on simple arcs, which it won't be the case in general. We will always consider arcs that can have self-intersections. But if you only consider simple arcs, then for a given pair of pans, there's essentially 6 simple gamma arcs up to homotopy, which are these 6 here. Okay, but as I said, our gamma arcs will be non-simple in general. And so given this definition of gamma arc, I can now tell you what the combinatorial lower bound that we use in our proof proved by Rodriguez Migueles is. So what his lower bound tells you is that if you want to estimate, give a lower bound of the volume of this three manifold, what you can do is you can just count the number of free homotopy classes of gamma arcs for every pair of pans in your pan decomposition. And if you can count that, you get a lower bound. So now, well, we want to use this result, and so we need to reduce the problem. So now we can reduce the problem to the problem of counting for one of these random closed geodesics, how many gamma arcs there are. So can we do some counting problem for the number of gamma arcs for a random closed geodesic? And to do that, we will use the other main ingredient of the proof, which are the mixing properties of the geodesic flow. So very briefly, so we look at the geodesic flow in the unit tangent bundle of the surface, and we use the property of the geodesic flow called measurable mixing. So what does that mean? So let's discretize things, and instead of looking at the continuous parameter geodesic flow, let's look at the time one flow map, where you just flow by time one every time, so you get a discrete dynamical system. And then being measurable mixing, what it means is that for any pair of measurable subsets, for all subsets of the unit tangent bundle, if you look at the probability of the intersection of t to the n of A with B, this is equal when n goes to infinity to the product of the two probabilities, probability of A and probability of B. So what does this mean intuitively? Intuitively means that if you think of A and B as as some subsets of the unit tangent bundle, and think of the event X, a point in the unit tangent bundle being in B, and the event t to the n of X being in the set A, these two events become more and more independent as n goes to infinity. Okay, and this is useful because once you know that certain events are independent, you can use that to estimate probabilities by multiplying. Okay, so that's one of the key things that we'll use in the proof. So what's the first step in the proof? The first step in the proof is going to be to try to get a lower bound for the number of gamma arcs for our random closed geodesic, which is denoted by this. And this lower bound, we call it f. F is a function of t, where t is the how long we flow along the geodesic flow, or in other words, the length of the curve. And how do we do that? We do that by ranking the orthogeodesics in the pair of pans decomposition. So we rank them by length, by hyperbolic length. So we get a list of all orthogeodesics in every pair of pans, ordered by length. And then we construct a partition of the unit tangent bundle as follows. So for every orthogeodesic, we look at the points in the unit tangent bundle, so that if you look at the geodesic generated by that point in the unit tangent bundle, that geodesic is in the homotopy class of a given orthogeodesic. So you fix the orthogeodesic O sub I, say, and then define the set BI to be, well, here's V, say, a point in the unit tangent bundle. You look at the generating geodesic in the unit tangent bundle by flowing forward and flowing backward. That gives you a geodesic in this corresponding pair of pans. And this geodesic is in the homotopy class of this orthogeodesic. So this tells you that this point B is in the set BI. Okay. And it turns out that this sets BI partition the unit tangent bundle at least up to up to a set of zero measure. And now we can reduce the counting problem of homotopy classes of arcs to a counting problem of how many, for a given point, how many of these VI sets does the orbit of this point visit? Okay, so you look at the unit time flow map for the geodesic flow, and then for every point V in the unit tangent bundle, we look at the points, this number here, the C sub NB, which is the number of different sets VI in this partition that the orbit of V from V to T to the N minus 1V visits. So every time this orbit visits a new set, you're adding a new homotopy class of arcs to your collection. And this is therefore increasing the corresponding volume, increasing the corresponding lower bound. So what we would like to find is a certain growth rate for the number of visited sets. Okay, so that for mu almost, or with respect to the probability volume measure in the unit tangent bundle from almost every V in the unit tangent bundle, we get that the number of visited sets is at least as large as that growth rate. Okay. And what we find is that if we take that growth rate to be of the order n to, well, there's this two constants playing a role here. This is delta over 2 eta. Delta and eta are some constants that come from the dynamics of the problem and from some geometric properties of the model. But the point is that both delta and eta can be made arbitrarily close to 1. Okay, so if you choose a growth rate for f that is of the order n to the 1/2, essentially, you can guarantee that for almost every v in the unit tangent bundle, you will have a growth rate of this order. Okay, and so using this, and how do we prove this? So the way we prove it is by using the mixing properties that I outlined before. So you will be dealing with these sets vi, and the fact that you have mixing is going to tell you that the events t to the nv visiting one of the sets vi are independent from each other. So that is helpful to compute probabilities. And then you also want to understand what the volume of these vi sets is as a function of the hyperbolic length of the corresponding orthogeodesic class. Okay. So I'm not going to get into the details of that, but these are essentially the main two ideas or ingredients of the proof of this proposition. And then once you have that, that gives you a lower bound of the number of homotopy classes of arcs, and you just hit it with Rodriguez-Miguel's lower bound, and that gives you a lower bound for the volume. Okay, so that's essentially the bulk of the main bulk of the proof is in this first step. Okay? And of course, hiding lots of details into the rock here. Yeah, so I think I'll stop with this, but I would like to mention a few questions or future work that we're looking into. So another interesting question we think is that, well, there are other possible models of random geodesics other than the one that we outlined. For example, one can use random walks on the surface group. And the question is, if you use that as your random model, do you get a lower bound of a similar growth for the volume? And another interesting question is, how does the volume of this hyperbolic three-manifold in gamma relate to the dimension or dimensions of other interesting complexes that you can associate to this curve gamma, such as the Segib complex? And then finally, let's not restrict ourselves to canonical lifts, but what happens if you study for a fixed geodesic the volume of all possible topological lifts? Does the canonical lift minimize the volume in that for that particular geodesic? And the types of growth results that we have, and I commented on in the previous remarks before, suggest that that might be the case. That in some sense, the canonical lift gives the slowest growing manifolds in terms of volume. For example, if you compare them to alternating lifts, that's certainly the case. Okay, so I think I'll stop here. Thank you for your attention.
Okay, let's thank our speaker.
Thank you.
So I had a question, which I think you sort of maybe answered with your question too there. Well, you answered the question with a question. I was going to ask if there's perhaps any other sort of complexity other than length of a curve that might be used. And I get, is that sort of the spirit of number 2 there?
Yeah, that would be one other possible complexity for the curve, studying the cube complex and the dimensions of the different cubes in the cube complex. I think that could give a lot of information, and it's probably a better quantity to estimate to get better bounds. Mm-hmm. Other things one can consider are self-intersection numbers of the curve, which this has been already considered by Tommaso Cremaschi and Andres Rodriguez-Migueles in a previous paper. And also for modular knots, one can look at the continued fraction expansion and the period of those. And Rodriguez-Migueles has also studied that. So yeah, there's many other notions of complexity. But I find this second one particularly interesting.
Mm-hmm.
Can I ask a question? Do you know if you give, let's say you take a genus 2 surface and you look at all of the various types of geodesics that you could pick on there, they're valid geodesics to get a hyperbolic manifold. Do you know what the least volume is that you get out of that?
I don't know, but that's an interesting question. Yeah.
Because it would seem like for every genus you would get, that question would be, it's sort of an interesting question.
Yeah. 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 I don't know, but that's really an interesting question.
Go ahead and jump right in if anybody else out there has a question.
I had a question. I think I blinked at one point and I didn't catch the definition of filling, although I think I got a rough idea. And so my second question is, what role does that play exactly? What happens if you don't assume it? But
right.
Definition, I guess.
Yeah. So so the key point why you want to consider filling geodesics is comes from this theorem by von Hasselblad here. So in order to get a hyperbolic surface, you need to assume filling. So if the geodesic is not filling, then you don't get a hyperbolic surface. So essentially, the way this theorem works is by using one of Thurston's hyperbolization theorems. Essentially, if this condition fails, then the hypothesis in Thurston's hyperbolization theorem also fails. So you fail, for example. So I'm thinking of, you need hypotheses like a toroidal, and so in this case, that would fail.
But can you say what filling is?
Sorry, yeah, I didn't say that. So filling, gamma is filling, means that, well, one way to say it is that if you look at the complement of so you remove so you take the complement of the geodesic, you get a union of these joint disks. Another way to phrase it is by saying that, so that's one way. Another way to phrase it is by saying that the geometric intersection number of the curve gamma with any other closed geodesic is positive.
Thanks.
Yeah, and sorry, Frederick, you didn't blink. I didn't define what filling is.
Okay.
Yeah, I was able to look that one up very quickly on my phone while listening to the talk. So, but I also guessed right. So, okay. Any